Okay, so let's start today's lecture. Okay, so before last lecture, right? So we have been talking about in the previous few lectures, we've been talking about the homogeneous equation. So x prime is equal to a of x with a certain initial condition, x of 0, let's say, is equal to x0. Okay, so these are homogeneous equations. And we've been talking about how to solve these homogeneous equations by saying that you consider the eigenvalue problem, A of x is equal to R of x, right? So you consider the eigenvalue problem. And once you consider the eigenvalue problem, you're going to consider several different cases, right? So basically, in order to calculate the eigenvalue, you would like to consider determinant A minus Ri is equal to 0. So based on R1, R2, if they're both real and they're distinct, then you're going to have you're going to find the eigenvectors, and you're going to say, let's say the solution is C1 e to the power R1t of x1 plus C2 e to the power of R2t of x2, right? So, and if you have like two eigenvalues, right? So if the two eigenvalues are equal and if they are real, then you're going to have another solution, right? So for the fundamental, for the general solution, and if they are complex conjugates to each other, then you're going to have another form of the general solution. Okay, so that's kind of what we have been talking about in our previous lectures. Okay, now this kind of equation is homogeneous. Okay, so this kind of equation is homogeneous, and we would like to consider from now the non-homogeneous equations. Okay, so the non-homogeneous equations. So that means its equation is x prime is equal to a of x plus some non-homogeneous vector g of t such that x0 is equal to x0. So we want to consider the non-homogeneous equations. Okay. Now, in order to consider the non-homogeneous equations, we would like to first consider the so-called fundamental matrices. Okay. So what is a fundamental matrix? Well, in order to consider the fundamental matrices, let us first work with a very general homogeneous linear equation that has the form x prime is equal to, okay, so let's say it is equal to p of t multiplied by x. Okay, so if you have this. Now in this case, we're going to look for a solution which is x of t is equal to x1 of t dot 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 up to xn of t. And we're going to have this vector matrix P of t is equal to P11 of t until you get P1n of t, and then reach the Pn1 of t until you reach the Pnn of t. Okay, so you're going to have such a matrix. Now, what happened here is that in general, you're going to find the so-called fundamental solutions. Okay, so right, so in general, you're going to find the fundamental solutions. That means the solutions x dxi over dt is equal to p of t multiplied by the vector xi, where I is from 1 to n. And we need the fact that, so we're going to find like x1 of t dot 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 xn of t. These vectors are linearly independent, right? So these vectors are linearly independent. Okay, so these are what we call them fundamental solutions. Okay, so now once you have the fundamental solutions, we can see that the general solution, okay, so the general solution, okay, so the general solution of this homogeneous problem can be written as x of t is equal to c1 x1 of t, right? So plus dot 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 plus cn xn of t. So they are linear combinations of the fundamental solutions. Is that good for everybody? Okay. So now there are two ways to check the fundamental solutions. If you still remember, okay, so the ways to check the fundamental solutions is to say that, okay, so let's say x1 of t up to xn of t, right? So they are linearly independent, right? So they are linearly independent from last lecture, we said that if and only if suppose, right? So suppose x1 of t multiplied by c1 plus dot 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 plus cn xn of t is equal to 0, then the c1 is equal to cn is equal to 0. So that's the first criteria for being linearly independent. And the second criteria is that you formulate the Wronski matrix, right? So the Wronski matrix is formulated as W of x1 of t dot 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 of xn of t. So that's the Wronski matrix, which is the determinant of this square matrix x1 of t up to xn of t. You're going to put the column vectors in a row. Okay, so you're going to put the column vectors in a row. So that means the x1 of t, xn of t, these are column vectors. So basically, it means that the x1 of t, right? So x1 of t is x11 up to x1n, right? So, and then let's say you're going to see that xn of t, right? So these are functions of t, okay? So xn of t is equal to xn1 of t dot 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 up to xn of t. Okay, so these are column vectors in a row. You put all these column vectors in a row, this is going to form a square matrix. And if the square matrix has a determinant that's non-zero, then we're going to say that the Wronskian is non-zero. Is that good for everybody? Okay, so these are kind of basic definitions related to linearly, fundamental solutions. Okay, so these are fundamental solutions. So once we have the fundamental solutions, we're going to form a matrix. Okay, so we're going to form a matrix. Okay, so which is called the fundamental matrix. Okay, so which is called the fundamental matrix, right? So what is a fundamental matrix? Well, the fundamental matrix means that you're going to form psi of t is equal to the fundamental solutions x1 of t up to xn of t. You're going to put all these fundamental solutions as column vectors in a row. So that's going to form a square matrix, x11 of t up to x1n of t, and then there are going to be xn1 of t up to xnn of t. Okay, so this is what we're going to call it, the fundamental matrix. Is that good, everybody? Okay, so now with this fundamental matrix at hand, it's kind of the criteria for the determinant. The Wronskian is just to say that the determinant of the fundamental matrix is not equal to 0. Okay, so that's about the fundamental matrices. Now so that's kind of going to be the definition of what we have for the fundamental matrices. Okay, so remember the fundamental matrix. Okay, fundamental matrix is just to first. Okay, so once you're given our homogeneous equation, you're going to find those fundamental solutions, right? So fundamental solutions, right? So you're going to find these fundamental solutions, which are going to be x1 of t up to xn of t. As long as you have the fundamental solutions, you're going to put all these fundamental solutions together and as column vectors in a row, that's going to form a fundamental matrix. So this is what we want to say about the definition of fundamental matrices. Okay, so fundamental matrices. So as a warm-up exercise, let us try this exercise. Okay, so here we want to say that can you find the fundamental matrix for the following system? Okay, so can you find the fundamental matrix for the following system? Okay, so you're going to have this kind of system. Okay, so I want to find the fundamental matrix for this system. So what should we do? Well, since you want to find fundamental matrix, it suffices to find fundamental solutions. So that means you're going to set A to be equal to 1, 1, 4, and 1, right? So that's going to be the matrix A. Now you want to calculate determinant of A minus the Ri. So that's going to be the determinant of 1 minus R, 1, 4, and 1 minus R. So here we can be faster at this level because you should get very familiar with what's going on in these lectures. So that's going to be 1 minus r squared minus the 4. So that's going to be r squared minus the 2r minus the 3. So that's r minus 3 multiplied by r plus 1 is equal to 0. Is a good family? So that means the first eigenvalue is 3, the second eigenvalue is minus 1. Now, corresponding to 3, you would like to calculate, right? So corresponding to 3, you would like to calculate those vectors, right? So that means corresponding to 3, you want to calculate the eigenvectors, right? So that means you want to set R1 is equal to R1 is equal to 3, and then you want to calculate the eigenvectors. So that means you want to set 1, 1, 4, 1, the matrix multiplied by x1, x2 is equal to 3 times x1 and x2. Is that good, family? Once you have this, it means that x1 plus x2 is equal to 3 times x1, and 4 times x1 plus x2 is equal to 3 times x2. So that's going to give you, okay, so that's going to give you x2 is equal to 2 times x1, and this one is just says that 4 times x1 is 2 times x2, which is the same thing as this first equation. So that it means that the first eigenvector, right? The first eigenvector. So let me call it x1. Okay, so the first eigenvector is going to be taken as 1 and 2. Is that good, everybody? So now we're going to find the second eigenvector. So R2 is equal to minus 1. Okay, so R2 is equal to minus 1. So that means you're going to have 1, 1, 4, and 1 multiplied by x1 and x2 is equal to minus of the x1 and x2. So that's going to tell you that x1, okay, so that's going to tell you that x1, okay, so plus the x2 is equal to minus of the x1, and 4 times x1 plus the x2 is equal to minus of the x2. So that's going to give you like x2 is equal to minus 2 of x1, and there's a 4 times x1 is minus 2 of x2. So you're going to have this. So that means the second eigenvector is also found. It's kind of equal to 1 and minus 2. So that's the first and second eigenvectors. Okay. So as long as you have the first and second eigenvectors, you're going to have the general solution, right? So the general solution, right? So the general solution of this problem is going to be given by x of t is c1 e to the power, okay, first eigenvalue is 3, so that's e to the power 3t multiplied by the eigenvector, okay? So eigenvector is 1 and 2 plus c2 e to the power minus t, eigenvector is 1 and minus 2. Okay, so that's going to be the general solution to this homogeneous problem. Now we ask what is the fundamental solution? Well, in order to calculate the fundamental solution, it suffices to see that this should be the C1 of the first fundamental solution plus the C2 of the second fundamental solution. So that means the first fundamental solution is going to be like e power 3t and 2 times e power 3t, and the second fundamental solution, x2 of t, is equal to like e power minus t minus 2 e power minus t. So that's the first and second fundamental solution, which means that the fundamental matrix is just equal to those fundamental solutions. You treat them as column vectors in a row. So that's going to be e power 3t, 2 times e power 3t, and then it's going to be e power minus t, and minus 2 e power minus t. Okay, so that's going to be the fundamental matrix of this problem. Okay, so this is kind of just to tell you that the fundamental matrix is just you put all these fundamental solutions as a column vector in a row. Okay, so once you put them as column vectors in a row, you're going to form such a matrix that we're going to call them the fundamental matrix. Okay, so that's what we call fundamental matrix. Okay, so this is about the fundamental matrix. Okay, so now we're going to kind of the natural question that might arise is that why do we need this fundamental matrix, right? So here let us recall the initial value. Okay, not just for general solutions, but for initial value problems. Okay, so let's say initial value problems. Suppose you are solving an initial value problem. That means x prime of t is equal to a of x of t, as well as the initial value, let's say x of 0 is equal to x0. Then you can see that we are going to say that x, okay, so of t, the general solution, okay, so the general solution, right? So the general solution is going to take the form x of t is equal to c1 of the first fundamental solution plus the c2 of the second fundamental solution. So these are the linear combinations of the fundamental solution, right? So that means you want to kind of put the value there. So that means you can solve this system. So that means let's say we solve. Okay, so here. So, so maybe I would just do a very general case. Okay, so let's say very general case. So that means here I'm going to have p of t and then dot 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 plus cn x n of t. Okay, so that's kind of very general case. Now you want to find the coefficient. So how do you find the coefficients? Well, there are two methods that you can find the coefficients. The first method is trying to say that you just put in two conditions here. X0 is equal to x0 is equal to c1 x1 of 0 plus dot 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 plus cn xn of 0. Once you have this, it means that you can find the unique C1 Cn because of what? Well, let me recall that okay, so if you have two pairs of choices, C1 x1 of 0 plus dot 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 plus Cn xn, okay, so plus Cn xn of 0, this is equal to x of 0, and then the C1, okay, so x theta of x1 of 0 plus dot 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 plus Cn theta of xn of 0 is also equal to x0, then you can see that C1 minus C1 theta multiplied by x1 of 0 plus dot 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 plus Cn minus Cn theta multiplied by xn of 0 is going to be equal to 0. And once you have that, because of linear independency, you see that C1 is equal to C1 theta until Cn is equal to is that good for everybody? Okay. So that's kind of going to give you the solution, C1 up to Cn from this linear combination. But how are you going to find the C1 and Cn? Well, to find the C1 and Cn, you're going to use the method 2. Okay, so to find the C1 and Cn, you're going to use the method 2, which means that you're going to treat everything. Okay, so you're going to treat everything as a system of linear equations. So that means you're going to say that x11 of t, let's say x11 of 0, right? So multiplied by C1. Okay, so I'm writing everything like this. Then is xn1 of 0 multiplied by Cn is going to be equal to x01, right? So, and then you have this system of linear equations until let's say x1n of 0 multiplied by C1 plus dot 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 plus xn of 0 multiplied by Cn is equal to x0n. And from here, you're going to treat the whole equation as a system of linear equations with unknown variables C1 up to Cn. So you solve for C1 up to Cn. That's going to give you a particular solution. Is that good for everybody? Okay. So these are methods that can lead to particular solutions for this typical problem. Now we're going to kind of use the fundamental solution, fundamental matrix. Okay, so let's say if you have the fundamental matrix. Okay, so if you have the fundamental matrix, right? So if you have the fundamental matrix, then it means that this is the matrix because I of t is equal to x1 of t up to xn of t. You put all these fundamental solutions as column vectors in a row. So that's going to kind of give you x11 of t until you reach x1n of t and then reach xn1 of t until you reach xn of t. right? So these are going to be those fundamental solutions. We put them as a column vectors in a row. Now you can see that the general solution has another very simple expression via the matrix vector notation. Okay, so the general solution has another very simple expression via the vector matrix notation. So because it is C1x1 of t plus dot 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 plus Cnxn of t, so that means it can, so here I'm going to say that I will write this one as, I will treat this square matrix as a row vector, right? So it is treated as a row vector, which means that this is a row vector consists of column vectors. So each component in the row vector is a column vector. So that's a matrix, is actually a vector of vectors, right? So now if this one is multiplied by C1 up to Cn, then by the standard vector matrix product rule, it means that you just product component wise, which you kind of form C1x1 plus Cnxn, you sum together. So this is actually a nice expression for the general solution, which is a linear combination of fundamental solutions. Now you take this fact that this first matrix is actually a fundamental matrix, and the vector C is actually C1 up to C. And so here I'm going to set, okay, so let's say we're going to set, okay, so set the C to be equal to C1 up to Cn. So that's kind of going to be a very simple formula for the general solution. Now, this simple formula is going to kind of lead to the particular solution very simply. Okay, so let's say so far what we have been doing here is that we consider this x prime of t is equal to pt of xt with a certain initial condition. X0 is x0. Once you have this, it means that our general solution, okay, so let's say our general solution has a very simple expression. It can be expressed as the fundamental matrix multiplied by an unknown vector C. So in order to find a particular solution, you can see that I can put initial conditions there. If x of 0 is x0, that's going to be equal to psi of 0 multiplied by C. So which means that the vector C as a vector, right? So the coefficient vector as a vector is equal to psi inverse of 0 multiplied by x0. So that's going to be a very simple formula. And therefore, you can see that the particular solution, right? So the particular solution is going to be expressed as x of t is equal to psi of t multiplied by psi inverse of 0 multiplied by x of 0. So that's going to be the particular solution for this problem. So that's going to be a very simple formula that instead of doing these two methods, either to use the linear independency to find a unique solution or to solve the system of linear equations, we can kind of express the particular solution in a very simple way once we know the so-called fundamental matrix. So that kind of tells us that the fundamental matrix, okay, so that this notion of this fundamental matrix is going to be kind of very important for simplification of the formulas that we have obtained in these lectures. So that's going to be a very simple formula to find those fundamental matrix. To find these particular solutions for homogeneous initial value problems. Okay. So that's once you have this, let's kind of walk through an example and see if we are able to apply what we have learned here. Okay, so here is a nice problem of this type. Okay, so let's say so let's say we consider this problem. Okay, so this problem is going to say that you're given, right? So let's say you're given a certain matrix 2 by 2. We know that it is the fundamental matrix for this non-homogeneous system. Can you solve the corresponding initial value problem? So you can see that the problem is nothing but saying x prime of t is equal to a multiplied by some x of t, right? So we are going to kind of, are you going to really work with determinant of a minus ri? is equal to 0, solve for the eigenvalues. Well, you don't, because here you know that the fundamental matrix is given. So that means if the fundamental matrix is given, okay, so that means psi of t is equal to e power minus t, 3 times e power minus t, and e power t and e power t. It means that this first column is the first fundamental solution, and the second column is the second fundamental solution. So you actually know the two fundamental solutions. So once you know that, it means that the general solution, right? So the general solution, okay, so the general solution is actually found. The general solution is given by x of t is equal to psi of t multiplied by some vector c. And the particular solution is also found, right? So the particular solution is also found. It is going to be x of t is equal to psi of t, psi inverse of 0 multiplied by the initial condition, which is initial condition. Is a good family, right? So this initial condition is x of 0. So once you know the psi of t, the only thing you need is to calculate this psi inverse of 0, and you don't know what this is. It's a good family. And how are we going to calculate? Well, remember, there is a very important formula. Okay, so recall there's a very important formula. Okay, so right, so there's a very important formula saying that if the matrix M is equal to A, B, C, D, then the inverse of the matrix M is equal to 1 over AB minus BC. That's a determinant of M. And then you switch the diagonal, okay, switch the diagonal, take a negative on the off diagonal. So that's going to be, this is going to be a very, very important formula that you're going to need it throughout the rest of the semesters, including exams. Is that good, family? Okay, so this is a very important formula for you to calculate inverse matrix. Of course, in order to guarantee that the matrix do have inverses, we're going to assume that the determinant is non-zero. Okay, so this is how you calculate inverse matrix. Now, once you know that, you can see that if psi of t is something like this, then you can calculate psi inverse of t is equal to what? Is equal to 1 of the determinant. This is determinant is e power minus t multiplied by e power t minus 3 times e power minus t multiplied by e power of t. Okay, so multiplied by e power of t. And then you're going to switch the diagonal. Okay, so e power t, e power minus t. And you're going to take a negative sign on the off diagonal. Okay, so you're going to take a negative sign on the off diagonal. So you're going to have something like this. Now, once you have something like this, then you're going to see that this is minus 1 over 2 of e power t and e power minus e power t and minus 3 e power minus t and e power minus t. So you're going to have something like this. Okay, so that's going to be psi inverse of t. So that's once you have this, you know that psi inverse of 0 is going to be equal to, so just put t equal to 0 here. So that's going to be minus 1/2. Remember, there's minus 1/2 as a factor multiplied in front of it. So that's going to be 3 over 2 and then 1 over 2 minus 1 over 2. So that's psi inverse of 0. Is that good, family? So as long as you have this, you can see from all these formulas that the particular solution, okay, so the particular solution is found. It's going to be x of t. Remember, the formula is psi of t, psi inverse of 0 multiplied by the initial condition. So the psi of t is going to be equal to e power minus t, right? So e power minus t and 3 times e power minus t as well as e power t. Okay, so and e power t. Now, psi inverse of 0 is also found. It's going to be minus 1/2 and 1/2 as well as 3 over 2 and minus 1 over 2. Okay, so that's psi inverse of 0 multiplied by the x of 0. X of 0 is equal to 2 and minus 1. So that's 2 and minus 1. So you have to just kind of expand this calculation. So that means you're going to have e power minus t, e power t, 3 times e power minus t, e power t, right? So now you calculate this product. Now you're going to have minus 1/2. So that's minus 1. minus 1/2, so that's minus 3/2, and then it's going to be 3 plus 1/2, so that's 7/2. Is that good, family? Okay, so as long as you have all this, you can see that the solution. Okay, so the solution is going to be given, right? So the solution is going to be given given by, okay, so the solution is going to be given by let me write it here. So solution is going to be given once you do this product, that's going to give you like minus 3/2 e power minus t plus 7/2 e power t, right? So that's the first solution. And then it's going to be like minus 9/2 of e power minus t plus 7/2 e power t. So that's going to be like the solution to this problem. The good family. Okay, so that's going to be kind of give you the solution to the problem. That's going to be a particular solution. The good family. So throughout this exercise, you can see that it is very important to be able to calculate Kasai inverse. As long as you have a 2x2 matrix, the very important thing is to use this formula to calculate. Remember, it's going to be equal to 1 over the determinant, and then you're going to switch the diagonal, and you're going to take a negative on the off diagonal. Okay, so you switch the diagonal, and you take a negative on the off diagonal. This is going to be very important formula that you must keep in mind how to use it. Okay, so once you have this, you can see that you even don't have to solve for the eigenvalues and eigenvectors, but you can directly apply this formula about particular solutions involving the fundamental matrix. So that's going to be kind of a very important observation for today's lecture. In order to find the particular solution, it suffices to know the fundamental matrix. Okay, so that's going to be the important thing for today's lecture. Okay, so here I'm going to make a few remarks before I close today's session. Okay, so the first remark is that if you choose the initial conditions such that the fundamental matrix is the identity matrix, then remember the inverse of identity matrix is still identity matrix, so that you're going to have the fundamental and the particular solution is just a fundamental matrix multiplied by the initial condition. Okay. And the second thing I would like to emphasize is an analogy. Okay, so the analogy is going to be something like this. Okay, so let's say here we are going to solve a system of homogeneous equations. Okay, so let's say dx over equal to a of x. Okay, so once you have this system, this equation, we are going to say that the general solution is equal to the fundamental matrix multiplied by other vector c. Is a good family. But if you kind of compare this equation with like the scalar equation, dx over dt is a of x, then you're going to see that x of t is equal to e power at c times e power at. But I'm going to write this c times e power at as e power at multiplied by c. Then you can see that the c corresponds to the c, the capital A, the matrix, corresponds to the scalar small a. So that means somehow you should actually replace the psi of t by e power at. Where this e power at, it means that you're going to raise the matrix A multiplied by t, you raise it to an exponential. So this is very hard to explain what this actually is. Is a good family. So that's why we introduced this fundamental matrices. Remember, the fundamental matrix is nothing but the fundamental solutions which are put as column vectors in the row. Is a good family? Okay. But this fundamental matrix, in a certain sense, is nothing but the exponential of the matrix. You raise a matrix to an exponential, that's going to give you the fundamental matrix. Is that good, family? Okay, so that's going to kind of give you an analogy of what we're doing in today's lecture. Is that we've been calling this fundamental matrix, but essentially it is the exponential it's the matrix raised to an exponential. Okay, so that's kind of probably all I would like to say for today's lecture. And in the next lecture, we're going to kind of make use of these fundamental matrices, and we're going to come back to the non-homogeneous equation, which means that the non-homogeneous equation, which means that it looks like this with a non-homogeneous term. Okay, we're going to kind of analyze how to find a solution to this non-homogeneous problem as long as we know the fundamental matrix. Okay, so that's what we are going to talk about in our next lecture. And so let me stop here for today's lecture, and I'll see you in the next lecture. Okay, so see you in the next lecture.